Section 10.2 Pressure. Among the most readily measured properties of a gas are its temperature, volume, and pressure. Many early studies of gases found on relationships among these properties. We've already discussed volume and temperature. Now let's consider the concept of pressure. In general terms, pressure conveys an idea of a force, a push that tends to move something in a given direction. Pressure P is, in fact, a force, F, that acts on an area A. Pressure is force divided by an area. Gas exerts a pressure on any surface in which they are in contact. The gas in an inflated balloon, for example, exerts a pressure on the inside surface of the balloon. Atmospheric pressure and the barometer. You and I, coconuts and nitrogen molecules, also experience attractive force that pulls towards the center of the earth. When a coconut comes loose from its place on the top of the tree, for example, the gravitational attractive force causes it to be accelerated towards the earth, increasing in speed as the potential energy is converted into kinetic energy. The atoms and molecules of the atmosphere also experience a gravitational acceleration. Because the gas particles have such tiny masses, however, their thermal energies of motion override the gravitational forces, so all the molecules that make up the atmosphere don't just pile up in a thin layer on the Earth's surface. Nevertheless, gravity does operate, and it causes the atmosphere as a whole to press down on the Earth's surface, creating an atmospheric pressure. You can demonstrate the existence of atmospheric pressure to yourself with an empty plastic bottle of the sort used to hold water or soft drinks. You can suck on the mouth of the empty bottle. Chances are you can cause it to have a partially cave in. When you break the partial vacuum you've created, the bottle pops out to its original shape. What causes the bottle to cave in is when the pressure inside is reduced, even by the relatively small amount that you can manage with your lungs. The gas molecules in the atmosphere are exerting a force on the outside of the bottle that's greater than the force within the bottle when some of the gas has been sucked out. We can calculate the magnitude of the atmospheric pressure as follows. The force F exerted by any object on the product of its mass times acceleration, that is, F equals ma. The acceleration given by Earth's gravity of any object near the Earth's surface is 9.8 meters per second squared. Now imagine a column of air 1 meter in cross-section extending through the entire atmosphere. That column has a mass of roughly 10,000 kilograms. The force exerted by the column on the Earth's surface is 1 times 10 to the 5th newtons. Figure 10.1, Atmospheric Pressure. Illustration of the manner in which Earth's atmosphere exerts pressure at the surface of the planet. The mass of a column of atmosphere, exactly 1 meter square in cross-sectional area and extending to the upper atmosphere, exerts a force of 1 times 10 to the 5th newtons. The SI unit for force is kilograms meters over second squared and is called a newton. 1 newton is 1 kilogram times meter second squared. The pressure exerted by the column of the force is divided by the cross-sectional area over which the force is applied. Because our air column has a cross-sectional area of 1 square meter, we have force over area equals 1 times 10 to the 5th over 1 square meter, which is 1 times 10 to the 5th pascals, or 1 times 10 to the 2nd kilopascals. The SI unit for pressure is Newton over meter squared, and is given the name Pascal after Blaise Pascal, a French mathematician and scientist who studied pressure. A related unit sometimes used to report pressures is the bar, which equals 10 to the 5th pascals. Atmospheric pressure at sea level is about 100 kilopascals, or 1 bar. The actual atmospheric pressure at any location depends on the weather conditions and altitude. In the early part of the 17th century, many scientists and philosophers believed that the atmosphere had no weight. Evangelica Torricelli, who was a student of Galileo's, proved it untrue. He invented the barometer, which is made from a glass tube more than 760 millimeters long that has closed at one end, completely filled with mercury, and inverted into a dish that contains additional mercury. Care must be taken so that no air gets into the tube. When the mercury-filled tube is inverted into the dish of mercury, some of the mercury flows out of the tube, but a column of mercury remains inside. Torricelli argued that the mercury surface of the dish experiences the full force or weight of the Earth's atmosphere, which pushes the mercury up the tube until the pressure exerted by the mercury column equals the atmospheric pressure at the base of the tube. So the height h of the mercury column is a measure of the atmosphere's pressure, and it changes as the atmospheric pressure changes. Torricelli's proposed explanation met with fierce opposition. Some argued that there could not possibly be a vacuum at the top of the tube. They said nature would not permit a vacuum. But Torricelli also had his supporters. Blaise Pascal, for example, had one of the barometers carried to the top of Puy de Dôme, a volcanic mountain in central France, and compared its readings with a duplicate barometer kept at the foot of the mountain. As the barometer ascended, the height of the mercury column diminished as expected, because the amount of the atmosphere pressure put down on the surface decreases as one moves higher. These and other experiments by scientists eventually prevailed, and the idea that the atmosphere had weight became accepted over many years. Standard atmospheric pressure, which corresponds to the typical pressure at sea level, is the pressure sufficient to support a column of mercury 760 millimeters high. In SI units, this pressure equals 1.01325 times 10 to the 5th pascals. Standard atmospheric pressure defines some common non-SI units used to express gas pressures, such as the atmosphere and the millimeter of mercury. The latter unit is also called the torr, after Torricelli. 1 atmosphere equals 760 millimeters of mercury equals 760 torrs equals 1.01325 times 10 to the 5th pascals equals 101.325 kilopascals. Note that the units of millimeters mercury and torr are equivalent. 1 torr equals 1 millimeter of mercury. We'll usually express gas pressure in units of pascal or kilopascal or torr, so you should be comfortable in converting gas pressures from one set of units to another. We can use various devices to measure the pressure of enclosed gases. Tire gauges, for example, measure the pressure of air in the automobile and bicycle tires. In laboratories, we sometimes use a device called a manometer. A manometer operates on a principle similar to that of the barometer, as shown in figure exercise 10.2.